As you learn how to process satellite imagery, one of the tools that you'll need to use is Gdal calc, which is a tool for doing raster algebra. When you're doing satellite imagery, you have to compute index like NDVI. That means you take two bands and compute the ratio of that. Or you may want to take some satellite data and rescale the values, or you have to combine two data and do some statistics. All of this are raster algebra operations, and Gdal calc is a very powerful tool that allows you to work with that. So let's just do a quick review of what raster algebra is and what kind of operations are supported with Gdal calc. So this is a script that comes with your Gdal installation. It is your raster calculator on the command line. If you used ArcGIS or QGIS or desktop software, you might have used a tool called raster calculator. And many people who just do GIS, they use kind of very basic functionality. You say, I have two rasters, I'll compute some ratio, or I'll take some values, divide by certain things. But the raster calculator actually can do very powerful things. Gdal calc, since it's a command line tool, it has got a lot of other features embedded, which are hard to do in a desktop environment. You can take one layer, apply some values, say, I want to change the unit of pixel value, I want to compute some transformations, or you can take multiple layers and compute some stats on that. Gdal calc can do conditional stuff. Check, create a binary raster. If the value is greater than this, select all those pixels. You can do logical things, select all the pixel values. If this and this is true, set it to 50. If this and this is false, set it to 100, right? You can do those kind of logical operations and mathematical statistical operations. One of the interesting things is that Gdal calc, being a Python script, it has got support for all the functions from the NumPy library. Python users will be familiar with this library. This is a numerical analysis library that people use in Python. It's very fast and efficient, and it has got all those functions for doing any kind of mathematical operations. So you can use all those NumPy functions within your Gdal calc command, and we'll see how that helps you in doing pretty advanced things. Where will you use this? Well, if you want to compute a spectral index, NDVI, NDVI, NDWI, you can use this script to compute your rasters. Reclassification, you can take your input raster and classify into multiple classes. Let's say you have an NDVI value, you want to break it into 5 classes. Or if you have data that was sent to by a vendor and say, this is my classification scheme, you want to transform them into different classes. So you can say class 1 becomes class 2, class 5 becomes class 2, and so on. You can do that reclassification using this. You can do pixel composites. I have one image for each month. I want to compute annual sum of precipitation. I have daily images. I want to compute monthly average, right? So with those kind of aggregations per pixel, you can do with Gdal calc. I found this interesting picture just yesterday on Twitter. Postholder user, heavy Gdal user, posted this. And again, this is quite proof of all the Gdal commands that we are learning, that you can do all of this in different ways. You can have a QGIS-based workflow, or you can write your custom Python script to do this. But you have Gdal calc or Gdal tools. All of that can be replaced by a simple command line tool and in a much more efficient way. So learning this will help you be more efficient. It'll help you reduce the amount of custom code that you have, and also it'll help you run things in production much faster. Right? So that's what Gdal calc is. It's a kind of a generic tool that allows you to do a lot of things. Let's learn how you can use this. Gdal calc allows you to specify one or more input files. So you can say, Gdal calc, I want to work with 2 files. You can say -a input1.tif -b input2.tif. So now if you want to do something with input 1, you'll refer to that as A. If you want to do something with input 2, you'll refer to as B. If you want to take ratio of input 1 and input 2, you'll just say A divided by B. So you'll do -a, -b, -c, all the way to Z. You can use small letters, so you can have that many inputs to your system. And you can specify an out file. You can say, whatever done with the computation, the result will go to the out file. And then there's a calc flag, which you can describe your computation. You can do things like A plus B divided by A minus B. So if you want to compute a spectral index, and the first band is NIR, second band is red, you can compute NDVI using this. So you can apply simple arithmetic operations. You can also do conditional operations. So you can have your expression like this, A greater than 1000. That means it's going to check this condition against every pixel. And if the condition is met, it's going to say 1. If the condition is not met, it'll be 0. So you can create a binary raster using this. You can combine multiple conditions using logical expressions. You can say logical AND, A greater than 100, A less than 150. So it's going to only match all the pixels between 100 and 150. You can do things like this. NumPy sum, A. A might be referring to a 10-band image. And you can say numpy sum is going to sum all the values of 10 band at that pixel. And typically in numpy, you need to specify axis. Axis 0 allows you to sum values from different bands of that raster. And all the creation options that we've learned, all the compression, etc., will be used by -co. Since it's a Python file script, the flags have to be double dash. So if you have a C binary like Gdal translate, there's a single dash. For the Python scripts, you'll have double dash. So a slight word of caution. Sometimes you write, so I've written my command, it doesn't work because Python scripts expect 2 dashes before each option. Okay, I'm going to show an example. We're going to do a case study on reclassifying. Let's say we have this elevation raster that we created in the first exercise. We have SRTM data, elevation data. The elevation is for Mount Everest region. So we have elevation from 0 to 8,000 plus, and we want to reclassify this. And we want to do something like this, that if the pixel value is less than 5,000, it should be 0. If a pixel value is greater than 5,000, it should be 1. I just want to create this binary raster. This will be useful as a mask. It'll be useful to find the region of interest and so on. How do we do this? So we can do this command. Let's just do it on the command line, and we'll come back and look at this command. Here, I'm going to load this data in QGIS. This is my merge.tiff. Okay, so we have this elevation values. You can see if I inspect each pixel value, this is the elevation value, and it goes from like low value to high value here. You divide this data into 2 classes, greater than 5,000, less than 5,000. We'll open a console. Let's just activate our Gdal environment. Go to downloads, Gdal tools, SRTM. So here we have merge.tiff. We can use Gdal calc, and we can say my input is A. So I'll say my A is merge.tiff. So I can now refer to merge.tiff by this letter A. Let's see what we want to do with this calculation. We'll say A greater than 5,000. That's our expression. So it's going to check each pixel value. If A, which is a merge.tiff, is greater than 5,000, it's going to assign 1. Otherwise, it's going to assign 0. And we're going to do out file is binary.tiff. Not going to compress it for now, otherwise we can specify that. Done. Let's go and check the result in QGIS. I have this binary.tiff. You can see what happened. I've got a binary file with zeros and ones. Here, this is 1. This is 0. You can see any value that was originally less than 5,000 became 0. Anything that above 5,000 became 1. So now we turn this elevation raster into 2-class raster. So if you want to mask certain areas, this is how you kind of apply your calculation and compute this binary. So let's come back to this expression. Say what really happened here is we have this expression that said, check each pixel value. If A is greater than 5,000, make it 1, else 0. So I can do something different. I can say, first, let me just remove this binary file. Or let's just try this. So I can say if A is greater than 5,000, I will multiply that with 100. So I'll say 100 into A greater than 5,000. What this will do is, first, A greater than 5,000 will create a binary values, ones and zeros. This will multiply this by 100. So wherever this condition matched, it'll be 1 times 100. So we'll get pixel values 100. Wherever it didn't match, it'll be 0. So now instead of 1, 0, we can get 100, 0. Let's see how this works. I'm going to name it binary custom value. So now I'm going to load this, and you'll see that now my values wherever the condition match is 100, elsewhere is 0. Okay? So this is one step where you can say, just don't do binary, multiply it by a number. So I get an output value, which is not 1, but multiplied by some value. So now we would say, I'll take this thing, I can multiply by some value, I can get a custom value. We can use this concept to now do a proper reclassification. Let's go back to our presentation. So for binary values, we learned we can construct a command like this, where our expression is A greater than 5,000. It'll be 1 wherever it matched, 0 it did match. Let's say I want to do it in multiple classes. I want to do reclassification where it's say less than 1,000 becomes 10, between 1,000 and 5,000 becomes 50, 5,000 to 8,000 becomes 75, and greater than 8,000 becomes 100. Okay? This is your classic reclassification that you do in raster data processing. We have some range of values, and now you need to take them and assign some other value. So how do we do this reclassification? We can apply the same concept and construct the command. Let's just do it. So we'll just say Gdal calc. Our A is still the merge.diff, and now we'll define our calculations. So first step we want to do is less than 1,000 is 10. So we can say if A is less than or equal to 1,000, this value should become 10. So I'll say 10 times this. And if I just ran this, it'll give me a raster where wherever it was less than 1,000 will become 10, elsewhere it will become 0. Okay, so that's my first part of the reclassification. I can say add. So that's one part of my final raster. I can add plus and I can add another condition. So I can say wherever A was greater than 1,000 and A is less than or equal to 5,000, I want it to become 50. So I can say 50 times both of this combined, right? This and this. I want both conditions to be matched. And then wherever this two conditions match, those pixels will become 50. How do I combine two conditions? Well, we just learned that Gdal calc supports this function called logical AND. So I can say logical AND, this, comma, this. So these are the two conditions. Both the conditions has to be true for this condition to be turned 1. And once it turns 1, we can multiply by 50. So that's our second part. We can do our third part. So we can say A has to be greater than 5,000 and A has to be less than or equal to 8,000. That will become 75. So I can do 75 into this logical AND. So this and this. And the last part, we can say A greater than 8,000 should become 100. And that's our calculations. And I'll just do my out file. We'll just say multi-class. And we can add other options for creation options. I'm going to apply the compression as we always do. So same compressions, just to say deflate, tile yes, predictor yes, right. And my reclassification is done. And one of the things you'll start noticing is very fast, right? We just classify this very large raster very fast. And come back here, let's look at the multi-class one. So we'll do 100 and we'll do multi-class 2. So you can see we have this classified raster where if I inspect the pixel value, wherever it is less than 1,000, you can see the value is 10, it's 50, when 1,000 to 5,000, here it's 75, and at Mount Everest, 8,000, it's 100. Right? So we just now take this our continuous raster and apply this classification into another value. And again, you can do the same thing if you just had, instead of a continuous raster, if you had a discrete raster, you'll just say A equals 1 becomes 5, right? B equals 7 or B equals 10 becomes this. This is how we do reclassification. And earlier we were talking about if you had a lot of kind of this conditions in a text file, well, just use Python or some of the scripting to construct this logical condition. And once you have this, you can always run this against your input and it'll classify your raster. Practical example where I did this, we had worked with a client who said we get data from this agency who sends us this classification data every 6 months. And we use our own model and they have this 100 classes that they send us. And we use a different classification scheme. I had to take this and convert it to our classification scheme. Well, you just have a command line here sitting like this. When you receive the data, run this. It takes the data from another classification scheme to your own classification scheme. I want to show you some more scripts that you can do, some more kind of things that you can do with Gdal calc. In your supplement here, we have this section here, calculating pixel-wise statistics on multiple rasters. This is doing the composites. People who are using Earth Engine, you're familiar with compositing. You've processed some raster data, time series data. How do you aggregate this? Here's an option how to do this. Let's say I have 12 rasters, and these are actual files. If you go and download some data from Prism, they'll send you one file per month. Precipitation for January, precipitation for February, and so on. You want to know what is the annual precipitation. So say I have 12 rasters. I want to get the sum of all the 12 rasters at each pixel. And that's my total precipitation. So you can just say, I have my Gdal calc, I'll read everything as A. If you read multiple files at A, it'll become like a multi-band raster. So this is, if you don't have a multi-band raster, if you have just files, you can just say this is all is my A. And I can say my calc is numpy.sum A. When you run this, you'll get per pixel sum of all the different files. Super helpful. If you have different multi-band rasters and you just say, I want a median value at each pixel, you can say numpy.median and you'll get the median value. An axis is the direction in which you want to sum the values. If you have rows, columns, do you want to sum across rows, columns, or in this case, Z direction. So 0 refers to stack of bands. Your stack of bands, you say sum across the stack of bands. You can sum across columns, sum across rows. So there's axis 1 and 2. So typically in your Gdal calc raster environment, when you use this, it's typically axis 0 because you want to sum across the stack of bands. There's also some other things. If you're multi-band raster and you can say I have RGB, I want to refer to first band, second band, third band. Gdal calc also has this another flag where you can say A band, B band, C band. So I have this raster RGB and I just want to use the band 1 as A, band 2 is B, band 3 is C, and I can do something with it. Another thing that you can do with Gdal calc that sometimes you require like a whole custom tool. So I'll show you this example. In our first exercise, we had done this hill shading, right? We had created this hill shade. So you get this black and white hill shade. And you can say this is nice. This gives you a kind of 3D effect of the terrain. And then we had done this colorization. You can say we can now take this elevation data and apply different color. Can I combine both? Can I take this color and apply to the hill shade? Can I get a colorized hill shade? This is something that, a lot of GIS packages have functions and tools built in to say colorize. I want to create a colorized hill shade. With Gdal, you can use Gdal calc. So if you see your supplement, there is option creating colorized hill shade. So what we want is like this: combine our hill shade and blend in the colors. So we have our two images. We have hill shade. We have this color. We can just use Gdal calc and just apply some formula. So if you look at the formula for blending two layers, this is the formula. You just can implement that as a Gdal calc expression. And now when you run this, say I will take the hill shade, I'll create the gamma hill shade from this, I'll take that and blend it with the output. So again, this is taking these two layers, applying some mathematical transformations, and you get this effect where you're blending the colorized hill shade. So you can do this in QGIS using blending modes. ArcGIS has a colorized hill shade function. But if you had thousands of them, well, just construct a Gdal calc command and you'll be able to do this. So if you had some complicated formula that you want to implement, you can now implement that and apply this on your data. Working on the next section, 1.4.3, where we can do some raster algebra, compute some band ratios. A brief primer on the spectral indices for people who are not from the remote sensing background. One of the core things that you need to do in remote sensing when working with satellite data is to compute these band ratios that highlight certain class of pixels. So if we take all the water pixels from satellite image and plot them, you'll see that their reflectance looks like this in different bands. Water typically has higher reflectance in green bands, absorbs most of the NIR in shortwave infrared light. So this is what it looks like. If you plotted all the vegetation pixels, it'll look like this. All the infrared values will have very high reflectance. Vegetation looks very bright because it reflects a lot of the NIR light, but it'll absorb a lot of the red light. So now if you want to detect vegetation from satellite imagery, you say, I'll take my raw spectral values. I have bands. I will take the ratio of the NIR and red band. All the vegetation pixels will have very high value. Rest, all the pixels will have very low value. And this is how I can separate vegetation from other classes. Similarly, if you take an urban class, urban pixels, built-up pixels will have very high reflectance in shortwave infrared, and it'll absorb some NIR light. And background will have different reflectance. So now if you want to detect vegetation, you can say this is a RGB image of a satellite data. If you compute NDVI, which is the ratio of the NIR to red band, this is what it'll look like. When you look visually looking at it, you can see this is the water body. This one is the vegetation. Both of them look green. But if you look at it as NDVI, you can see this is visualized as white to green. Water will look have low NDVI. This one is high NDVI because this is vegetation. Right? So this is useful to separate vegetation with non-vegetation. So let's learn how to compute this kind of band ratios and index using Gdal. The ratios are typically done in a normalized form. So instead of dividing NR by red, you say NR minus red divided by NR plus red. That means the output is always between -1 and +1. So you can now attach some meaning to the output values. So let's run this first command. We will take one of the stats and we'll compute the stats. You can see the range of the values are from like 0 to 1. And here is the no data value of this particular data. When you're doing any raster algebra using Gdal or QGIS, because QGIS uses Gdal in the hood, no data is very important. The way the raster calculators are set up is if there are 2 pixels, and if one of them is no data, the output will become no data. So you need to make sure you specify the no data correctly and they are treated in the right way. So always when you're working with the satellite data, doing some band math, make sure you always specify the no data. Here, all our bands come with no data value of -999. So we'll keep that in mind. We're going to use this tool called Gdal calc. Let's learn more about this. Gdal calc is a very powerful raster calculator that comes with Gdal. You can do all sort of math operations with different bands of image. It supports different syntax for doing band math. You can do very complicated math as well. I'll show some example as well. But one important difference you'll notice is this is a Python script, gdalcalc.py. It comes with a Gdal installation, but it's a Python script. So when you want to run it, you want to make sure your Gdal installation can find the right Python binary to be able to run this. For Mac or Linux users, mostly you can just type gdalcalc.py and it'll just work without any issues. For many of the Windows users, depending on your configuration, you may have to specify an extra option to say, use the current version of Python in the current Conda environment. So if you see the commands, you will have this prefix here, which says Python, Conda prefix scripts, gdalcalc.py. This is the location of the script. Conda prefix will say, what is the current Conda path? Where is the current environment installed? You'll get the path on the disk. There's a folder called scripts. Within that, there's a gdalcalc.py. So Windows users can run this command. Mac or Linux users can just type gdalcalc.py and you can run this. The way gdalcalc works is you have gdalcalc, you have the expression that you would say, this is the calculation expression, and this is the output file. And you can specify the input files with this prefix -a, -b, -z, up to -z. So you can say -a is this file, -b is this file. And then you can say a is this, b is this. This is the expression you can do. So in our expression that we want to do, we want to compute NDVI. So we say gdalcalc -a is our NIR band, which is the band 5. -b is this file with the red band. The expression we want to compute is a minus b divided by a plus b. And when we do this, we want to make sure we set the no data correctly, whatever was there for the input data. Yeah. So let's try and run this and see if you get the NDVI image. Windows users, if you get error with this, just try from here, gdalcalc, and it should work. But I think most users, you have to specify the full path to the Python file. When using Gdal Python scripts, you make sure you prefix it with this so it can find the correct place to launch. And this is what it looks like. The NDVI image is just a single band image. So by default, it will be visualized as white to black. Black is the low values, white is the high values. You can see the water has very low NDVI. So if I inspect this, you'll see this is -0.17. NDVI ranges from -1 to +1. Here, there's some vegetation. If I inspect this, you have a high value of NDVI. And now you can see all the vegetation will have high values. The non-vegetation will have low values. Clouds are kind of outliers. They have very high values in NDVI. Typically, you apply a cloud mask. So you remove the clouds, and then you would be able to run this. We have a single band image. If you want to visualize this in color, we can apply some color visualization. We can do this in QGIS. You can say, I want to visualize this as from, let's say, white to green, right? And now we have this representation of this, but low values are white, high values are green, and so on.